Alright, hey y'all, it's Mr. Slacker, Myers Mathematics, and let's just jump into it. We're gonna look at, for each of the following sequences, whose nth terms are indicated, state whether the sequence is bounded, and whether it is eventually monotone, like how my voice probably sounds today, increasing or decreasing. So, let's go ahead and look at this first one here. We've got in and a sub n, which is this whole thing right here. Okay. Well, we're not starting at 1 or 2. Normally we would start at 1, but this says in greater than or equal to 3, which means we're starting at 3. And then that would be 3 to the negative 1/3 power, which is a pretty crazy number. That would be 1/3 to the 1/3 power. Interesting. 1/3 to the 1/3 power. Or you could say like x to the x power, but it's not quite like that. It's similar to the previous one we were doing, but the graphs are going to look a little different. So this will be 4 to the negative 1/4 power, which is just 1/4 to the 1/4 power. Now that one you probably could do a little bit of it by hand, because you could take the root would be 1/2 and then another square root. So a fourth root, a 1/4 power is a fourth root, or a radical with a 4. That would be like taking the square root and then taking the square root again. So if I take the square root of 1/4, I would get 1/2. And then the square root of 1/2, I don't actually know what that is, but the square root of 2 is about 1.4. So it'd be 1 over 1.4. So whatever that is. And so on and so on. I think the first one that we'd be able to actually evaluate by hand might be like 16. 5, skip a few to 16. So this is 5 to the negative 1/5, which is 1/5 to the 1/5. And I'm not putting a parentheses on it, but I guess there probably should be a parentheses on the 1/3, 1/4, and 1/5. 16 we would probably be able to do, I think. No, because it's the 16th root. So if we started at 1, 1 would just be 1. Like it's 1 to the negative 1 over 1. So it's 1 to the negative 1 power, which would just be 1. But yeah, so it looks like we're not really going to be able to, because 1/16 to the 1/16 power, the 16th root. Yeah, not sure. But it's probably going to, just like how it was x to the x power in the previous one, even though the number's getting smaller, the root is also getting smaller as well. Normally you need a number that's, if you're going to times a number by itself over and over and over again, if that number is more than 1, then it increases. But if it's less than 1, it decreases. If you take a number that's just a little bit less than 1, like 0.9, if you times it by itself, you get 0.81. Then times it by itself again, you get like 0.729, and so on and so on. So if you times a number that's just a little bit less than 1 by itself over and over and over again, you'll eventually get a really small number. And so that's kind of what's happening, is that we would be taking a number that's coming up to the value of 1, but the more of a root it is, the more it's like it can get closer to 1, but then the smaller the power it is, the less amount of them there need to be, but like it's going towards this power of 1/16. Exponentials tend to have more strength than, like, bases that are just increasing by 1 at a time. So it would be basically saying like, okay, so if I take 0.999999 and I times it by itself a bunch of times, then I would get a small number. Whatever the base number is becomes relatively irrelevant. So then as we go to infinity, it's just going to be 1. So the limit is going to go to 1. You can kind of look at the graph to figure that out as well, if you're allowed to graph it. I actually have the graph pulled up. That way I can show what some of these values might be. So like 1/3 to the 1/3 power, I would be plugging in 3. And that is 0.693. We'll do 3 decimal places, just so you can see what's going on here. 0.693. And then 4, let's see if it gets closer from 4. 4, 0.707. And on the graph, actually, there's a minimum, actually it's an absolute minimum at e. So that's probably why they're having us start at 3, is because the function is actually only increasing once we bottom out at e, which is about 2.7. So starting at 3 and beyond, it's only going up. So that way we can start answering questions like, is it bounded and is it monotone, increasing or decreasing? Let's just do the values that we have in the chart real quick, and then we'll get to the actual answer of the question. This is 0.725. 725. And then 16, this should be getting pretty close to 9. Not super close. It's taking a while to get to 1. 0.856. So it is getting there. Let's just see what would happen. Let's say I do 1,000. F of 1,000. So that would be 1 over 1,000 to the 1 over 1,000 power. And now we're at 0.993. So that's pretty far, right? I'll actually put this into a column here. This is going to be 0.993. So at that point, we are almost at 1. It is going really, really slowly towards 1. It's really bottoming out slowly towards 1. So, yeah, and I meant to put a little till in front of all these other numbers because those are approximations, right? Not the actual numbers. But, yeah, so there we go. So the sequence is bounded. It is especially going to be bounded if it has an asymptote, but it doesn't necessarily have to have an asymptote, as we saw with like sine and cosine waves. They have tops and bottoms, so they're bounded above and bounded below, which we just call bounded. This one, I mean, so it depends on how your teacher wants you to answer the question. N equals 3 is going to be the lowest value on the interval from 3 to infinity, counting by ones, or even not just counting by ones. So if you want to say that it's bounded below by 0.693, I wouldn't. I think that most textbooks would not, unless it's like a definite thing, and it's not just because you're capping your interval at a certain place. We wouldn't say it's bounded that way. So I would say it's bounded above by 1. Bounded above. Bounded above by 1. So that it doesn't go above 1. Now, if you wanted to list an interval of values, it would be something like 0.693. Roughly, if you wanted to put the actual number there, you would put 1/3 to the 1/3 power. But then it's going all the way to 1. It's never actually reaching 1 because remember, infinity is not a number. If it were able to go to infinity, then it would go to exactly 1, but it's not able to go to infinity as a number, right? Like if you did a Googleplex, then it would be really, 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 really close to 1. It'd be like 0.99999, like a million nines. But it wouldn't be 1. It's not 0.9 repeating. It's just a lot of 9s if you went to a really, really large power. So it's not actually going to reach 1, but it'll get infinitely close. It'll approach it as we go to infinity. Is a better way to say it. Anyways, so bounded above by 1. It is monotone, and it's monotone increasing because it is going up. Monotone increasing, right? And I've said this in other videos, but it can be monotone increasing, decreasing, or stagnant if it's a constant. Typically, there's a couple other cases I think where it might be stagnant, but a constant would be the most obvious option. It's just a horizontal line graph. That would be monotone stagnant, or at least that's what I would call it. But typically, it's always going to be increasing or decreasing if it is monotone at all. So it is monotone and it's monotone increasing, and that about does it for this video. Hope that was helpful. Check out the 5 math mistakes everyone makes and how to avoid them on my website, Myers Mathematics, and I'll catch you guys in the next video. Blessings, y'all.